We go, recording started.
So I don't need to remind you to unpause.
No. Hello, everyone, and welcome to Klara's webinar, OpenZFS Data Protection, Best Practices for Keeping Your Data Safe. So let's get started. As a quick overview, here's the things we're going to go through today. We'll start off with introductions, introducing myself and my co-host JT. Then we'll talk about understanding the threats to your data and what could be happening there and what we can do about it. Then get into more details about how to deal with it, including how ZFS ensures data integrity in the first place, best practices for replication and backup, then specifically strategies for dealing with ransomware, and then choosing the right snapshot regime for your workload. Then we'll answer some questions and move on from there. So to start with introductions, hello, I'm Allan Jude, co-founder of Klara here, and I'm our ZFS engineering manager, and I'm joined today by JT Pennington.
Yeah, so I'm a ZFS solutions engineer here at Klara, and I'm a longtime Linux and BSD user and developer. So thanks everybody for joining us.
Yeah, so let's start off by talking about what are the different types of threats that are faced by your data.
Yeah, so there are different types of threats that can compromise data security, including malware, human error, data breaches, etc. We're going to break them down into kind of 5 categories: faults, nature, mistakes, ransomware, and threat actors. So faults would be hardware failures, and these come in all shapes and sizes. It usually can be solved by actually swapping out that component. Then there's software failures, and they're usually a little bit trickier to diagnose and resolve. And then between the two, you have firmware. The firmware's even more of a trouble because most of the time it's not open source, so it's kind of all black magic. For nature, data can be destroyed or taken offline by natural disasters, anything from a power outage, earthquakes, floods, hurricanes, anything like that. Fires are also another one. There's been several data centers that have caught fire, and if that's the only place where your data is, well, it's going to be lost. Mistakes. So users and administrators can accidentally delete, corrupt, modify data they weren't supposed to, and otherwise lose the data that they were trying to protect. Ransomware is untargeted attacks that are done by threat actors seeking to take your data hostage because they want you to pay them to get your data back. And speaking of threat actors, there's also the advanced persistent threats that are threat actors that are actively targeting your organization because they want to steal or destroy your data, either because they want to be able to take advantage of your data, or if they're related to a competitor and they want to be able to injure your company.
Yeah, and especially on the ransomware front, we actually see ongoing situation right now with Western Digital, a company that makes almost half of all hard drives that ship, is currently, having their network compromised and ransomware and being demanded an 8-figure ransom to get their data back. And that's having widespread impact, not just on their cloud services and so on, but even just their ability to provide support to their customers because all their internal infrastructure is offline. So looking at when is your data actually at risk? And the short answer is that it is always at risk. And it's just how many steps and how many layers have you taken to mitigate that? How at risk your data is probably mostly proportional to your RPO, or recovery point objective. That is how frequently you are doing backups. And the biggest factor there is if you're doing backups only overnight, for example, as was commonly the case, then that means if the malware strikes at the end of the day, then your backup doesn't include everything you did today. And so not only do you have the time it takes to restore and get things back to working, but you also just wasted all the effort of today. And that was all undone, and that can cause all kinds of other problems. And so we'll talk more about how to mitigate that and some strategies around that later in the webinar. But your data can also be at risk if your backup or replication system just propagates the damage, right? As we talked about, if your backups don't have a history, they're just one copy, then if someone accidentally deletes or damages a file, then once that's been backed up, now your backup copy or your replica also has the same damage, and you don't have the ability to undo it. And again, we'll talk more about how to deal with that.
Yeah, so let's look at some of the different ways that ZFS can protect your data. There are four main points that we're going to cover here. The first is checksums, end-to-end checksums. So ZFS uses per block checksums, which allows ZFS to be able to verify the integrity of every block to prevent bit rot. The second way that it can protect your data is volume parity. So RAID Z does not have a write hole like RAID 5 or RAID 6. Write hole being when there's a power failure or something like that, and only partial data is written. And the strong checksum ensures that ZFS can determine which side of the mirror contains the correct data. The third way is through metadata redundancy, and this is entirely controllable by the user and the administrator. So you can control the redundancy from all to most or to some. So that would be all of the file, part of the file, or some of the file. And of course, that's available in the data sets. And the last is the copy on write feature that ZFS uses, meaning it's always moving from one consistent state to the next, meaning that FSCK is not needed and you don't have to worry about shorn writes where only part of a multi-sector update is actually successfully written to disk.
Yeah, and that can be a big one because with your traditional file system, if you're modifying a file when the power fails or the system crashes or whatever, if you're partway through writing that file, what exists in the file system is now the first half of the new version and the second half of the old version. And together that might not actually be usable. With ZFS, we're always writing the new version to a second location and then updating the file system to point to that location once that's done. So if the process stops anywhere up until that is completely finished, then when you come back, you're at least going to have the unmodified, undamaged original version rather than nothing at all. And that makes a big difference. And that's part of why it doesn't suffer from the hardware RAID write hole. With hardware RAID, because it's writing the data and the parity as two separate steps, it doesn't matter which order it does it in, but if both steps don't complete, then if you go to rebuild this array later, then those two numbers aren't going to match. And when it tries to reconstruct, it'll reconstruct the wrong data, but have no way to know that that was the case. Because ZFS has these end-to-end checksums, it'll be able to say, oh, that doesn't turn out to give us the right value. I will try different combinations and find something that will, or at least say, okay, we know for sure that file is damaged. And that's where, again, that end-to-end checksum comes in because you can do a better version of a patrol read that hardware RAID can do in ZFS called a scrub, where we're going to read every block and verify that the checksums still match. So we can detect that something didn't get updated or some hardware flipped a bit or whatever, and repair it while we still have enough parity, not allowing errors to build up over time until we actually do lose data. So now let's look at those more detail on those volume parity options. So the first is a mirror. This is the most simple type of parity where we're going to have multiple disks and we're going to write the same data to every one of those disks. So as long as we still have one of those disks, we still have all the data that was written to this mirror. And all of these ZFS parity types offer advantages over hardware RAID. Coming from those strong checksums, it means we can distinguish when something is wrong. So if you have a hardware RAID mirror, then when you're writing data to both halves, if something goes wrong with one of those drives and it doesn't record the data correctly or loses the data over time, when your array goes to read it, it just picks one of the members to do the read from and assumes that it's right. With ZFS, we then verify the checksum. If it's not right, we can read from the other side of the mirror, ensure that that's right, and then update the failed side of the mirror and get everything back to working, where hardware RAID has no abilities to do that. Another really interesting thing that RAID Z can do is incremental recovery. So if a drive is offline for just a minute or two, hardware RAID has to assume the drive that's coming back is an entirely new drive and rewrite all the data. So if it's a 20 terabyte hard drive, you're going to have to resilver all 20 terabytes of content. With ZFS, you have this dirty time log or DTL that knows this hard drive has all of the data up until 4 minutes ago. I can just replay every block that was modified in the last 4 minutes to it and get it caught up. And so in a couple of minutes, your array is back to perfect health versus having to wait for a resilver across an entire 20 terabyte disk. As we mentioned, RAID Z is ZFS's kind of version of RAID 5 and 6, but it's much better. As we talked about, no write hole from hardware, but it also has the option of triple parity. So that's RAID Z3, which isn't available in hardware. So that means you can have an array where you can lose up to 3 disks from the array and still be able to operate. And that's per RAID Z, whereas normally your pool is going to be possibly be made up of multiple separate RAID Zs, each that can lose 3 disks. And it gives you a lot better control over the amount of parity you have to ensure that your data doesn't go anywhere. And another thing, because of the way ZFS works, being a combination of the volume manager, that is doing the RAID, and the file system, when you do have to resilver a disk, ZFS knows which space on the pool is allocated and which space is still free space. And it doesn't have to resilver that free space like hardware RAID does, because it doesn't know which blocks are allocated from the file system and which aren't. This allows ZFS to have a faster resilver because it only, if your pool is only 20% full, it only has to rewrite 20% of the data, not the full 100%. And ZFS also has DRAID, or distributed parity RAID. One of the downsides of any type of RAID array is that when a drive fails, you're pulling from the other members of that array to rebuild the failed drive. In DRAID, we make a complex array by instead of taking a bunch of separate RAID Zs, and if a disk fails, you use just the disk within that RAID Z to recover. DRAID will make up each of those different RAID Zs from pieces out of all of the disks in the pool. So, if you have 100 plus disks, then when one drive in a normal RAID Z setup, you would have split that into 10 RAID Zs of 10 drives each. And so when a drive fails, you'd be reading from 9 disks and writing to 1. With DRAID, you're going to be reading from 99 disks and writing to 99 disks, because the spare that you're replacing the failed disk with is also distributed across all the remaining drives. And so you can imagine the difference in performance for a resilver of reading from 99 disks and writing to 99 disks versus reading from 9 disks and writing to 1. There's a lot fewer bottlenecks in there. So it only makes sense at really large scales, but it does mean that you can build machines that can recover in much lower time, especially now that we're looking at hard drive sizes getting into 50 terabytes by next year. That's going to be a lot to resilver when you consider you're building an array of tens and hundreds of these disks.
So now that we've touched on data integrity, the question needs to be asked: if you're protecting your data with backups, what are you protecting your backups with?
Yeah, and so that brings us to encryption. So most encryption, like whole disk encryption, whether that's LUKS or GELI or self-encrypting drives or whatever, the point of these is that they're protecting data at rest. And so in your laptop, that maybe makes sense, right? When the laptop's powered off is probably when it's going to be stolen, and it means that the data can't be accessed. But in a storage server, your storage server is usually not powered off. And so if it's never powered off, then the data is never at rest. So is it ever actually protected? And so ZFS allows some more flexibility here. Instead of having an encryption key per disk or as part of the file system, it does it at the dataset level, which means you can have some data with one key and other data with another key. And when you're not using the sensitive data, you can unload the key from memory, and that data is now at rest and fully protected. So by splitting your data into different data sets, each using separate encryption keys, it means that you can actually put selectively some data at rest and other data still being active. And only when the encryption key is loaded can the data be accessed or modified. Also, ZFS is using its strong checksums. It actually splits that 256-bit checksum in half and stores half of it as the checksum of the encrypted data as it is on disk, but the other half is a message authentication code of the plaintext data. So ZFS can detect if the data has been maliciously modified and say, no, that's not actually the data we originally written. And that means it can detect, you can only generate the correct message authentication code if you have the encryption key. ensuring that it will actually detect if somebody tries to maliciously modify the data, plus the regular checksum ensuring that the hardware didn't accidentally modify your data. And so this ability to put the data at rest can provide a lot more protection than your typical self-encrypting drive or normal block level encryption. The other advantage of this is the ability to permanently destroy data, especially now that we have flash-based storage where, just because it's the millionth sector in the disk doesn't actually mean it's going to be at the same offset within the disk, like on a hard drive, meaning that even if you purposely erase all the data on a hard drive or overwrite all the data, it doesn't actually mean all of the data is gone because SSDs are over-provisioned or under-provisioned. They're actually bigger than the size they advertise so that they can replace cells as they fail. But it means because of that wear leveling, just because you overwrote the data doesn't mean that there's not some of that data still remaining on the hard drive. So by using ZFS encryption on different data sets, we can decide at some point, okay, this data we need to never be accessible again. We're going to unload the key and destroy it. And now no one has the key to decrypt that data and it's unrecoverable. And you don't have to worry about trying to overwrite it or use the, self-encrypting drives and rotate the key and so on. It works the same way as self-encrypting drives and rotating the key, but allows you to do it for different data sets. So if you only need to destroy a portion of your data, it gives you that flexibility. But the other big thing is the ability to do encrypted replication. So ZFS raw replication allows us to send a backup to an untrusted site. So we're actually making sure that the data we send, that we're serializing and sending to the other host, is in its encrypted form, and we're not sending the key. So this other host that you're backing up to doesn't have the decryption key, and so can never mount the data. But you can send the encrypted data back to the original host as a restore operation, and then load the key, and you'll have access to your data. This way you ensure that wherever your backup is doesn't have to be a trusted site because all they ever get is encrypted data. So someone from one of the viewers asks, how are you sure that the key is destroyed? That's partly on your key management policies. Generally, what you want to do for that is have a key file that's stored securely and that you can ensure that you've overwritten and destroyed. But as long as nobody has the ability to do that key, which, using a combination of key files and passwords or whatever, will ensure that that data can never be decrypted again once you've destroyed the key file. But yes, it is a little bit of an exercise to the reader. And if you want help setting up something, then do get in touch. There's contact information at the end of the webinar.
So before we talk about best practices, let's take some time and define two of the terms that we're going to be using. One of them, go ahead.
I was going to say, we just briefly touched on a bit of replication, but let's dig into how to best use replication as part of a backup policy.
So we already touched on recovery point objective earlier, but I'll recap it here. And that is how much data is going to be lost by reverting to a backup. So if you're doing, as Allan mentioned earlier, if you're doing backups at the end of the day, you potentially could be losing all the data that you had that day. So controlling your backup frequency and duration will change the amount of this. The second is RTO.
Before the one thing I was going to say there is, oftentimes with traditional backup systems, the limitation on your RPO is how long the backup takes, because you can't really start a second backup until the first one is finished. But we'll talk about how with ZFS, we can avoid some of that problem.
So the second one that we're going to be talking about is RTO, which is recovery time objective, and that is how long it takes to complete the restore from a backup. Now, this is going to depend on a couple things. Number one, the amount of data, the volume of data that you actually are restoring from your backup. And two, of course, how fast you can do that. If you're going over a 1 gig line, that's going to take a bit longer than if you're transferring over a faster line. And if this is a remote, then obviously you have other issues to take into consideration as far as, traffic, internet traffic. So now that we've got those two terms explained, let's talk a little bit about how ZFS can help with these.
Yeah. So there's two big components of ZFS that we would use in building a backup system. The first are ZFS snapshots. So at any time, you can take a snapshot of the file system, and this gives you a point-in-time view of that file system, but also ensures that that file system is consistent. So when you take a snapshot, you get how every file in that file system looked at that exact moment. And so this is a big boon for backups because one problem with traditional file system-based backups is getting a consistent view of the file system while it's in use, right? People are doing work while you're trying to take this backup. So technologies like volume shadow copy allow us to copy or to back up a file while it's being used by basically doing a similar thing to this and having a snapshot of that file and getting, the whole file is from this one time rather than, if it was a many gigabyte file while you're backing it up, if somebody changed something at the part you've already backed up, you're not going to pick it up yet. And then they change something that you haven't backed up yet. And now you have the version of the file you would restore from backup isn't from the beginning of the backup or the end of the backup. It's a mix of the two. And that is almost like a shorn write when the file system fails. And so we don't want that. So by having a snapshot, that would give us this consistent view of the file system that we can then take the backup of, knowing that nothing in that snapshot is going to change and we'll get a consistent backup. Volume shadow copy is nice to be able to back up individual files that way, but it doesn't actually provide you a view of the entire file system, whereas a ZFS snapshot does. And this is especially important when you have interdependent files. Like, for example, in a database, if each table in the database is a separate file, then you can end up with foreign keys where, we backed up table 1 and then table 2. And before we backed up table 3, we did an insert that added dependent rows in all 3 of those tables. And we back up table number 3, and it references stuff in table 1 and 2 that wasn't there when we backed them up. And so now our database is inconsistent, whereas a ZFS snapshot will prevent that. But the main reason we're talking about snapshots here is because that's the required building block for ZFS replication. So ZFS replication allows us to serialize a file system into a data stream. So we can take a file system, serialize it into a data stream of here are all the objects and all the metadata, and send that over the network or any other method we want, and recreate that file system on another machine in a way that's compatible so it can cross entire machines and operating systems and hardware types. And by doing that, and then what makes ZFS really special is its ability to do that incrementally. So you take a snapshot and you replicate that to the remote host, and then you take a second snapshot and you can replicate only the blocks that have changed between those two snapshots. Right? Each of these snapshots is a point in time, and by knowing that time range, ZFS can quickly grab all the data modified in that time range. Whereas a normal file-based backup system is going to have to go and look at every single file and be like, did you change since last time? Did you change since last time? And that can take a long time just to find what data needs to be backed up. So even if the amount of data that has to be copied isn't very large, the backup can still take a long time because you have to check every file. With ZFS, because we're combining the volume manager and the file system, it can very, very quickly find just the data that's changed and send it. This especially avoids getting bogged down with those metadata operations and examining a large number of files. So if you have a lot of small files, ZFS replication is still, its time is just proportional to the volume of data that needs to be replicated, whereas other backup systems are going to be slowed down by the sheer volume of the number of files. So now that we've talked about what snapshots and replications are, let's apply these ZFS features to a backup scheme. So the first place where snapshots help us are the RPO. As we talked about, the biggest thing holding back us having a very frequent recovery point objective, of saying, whatever happens, we don't want to lose more than an hour of our work. That would require you be able to finish a whole backup in less than an hour, which with most traditional backup systems isn't necessarily going to be possible. But with ZFS and snapshots, it is, because we can create the snapshots practically instantaneously. And we can keep many of these snapshots, and we'll talk about retention in a minute. But this means that we could take snapshots every 5 minutes, and meaning that if we do have to roll back because ransomware hit the system or somebody just accidentally deleted a file, we can roll back to any one of those 5-minute snapshots for however long we retain them. And more importantly, with ZFS, you can access a snapshot as a read-only copy of the file system. So if it was just one file that got accidentally deleted or corrupted, you can restore that individual file and not have to roll back the whole file system. But we'll talk more about that as well. So we can create very frequent snapshots to get very, very short RPOs. Then our RTO can also be sped up. Because we can roll back a file system to any one of these snapshots instantaneously, it means our recovery time objective can be less than a minute. So we can get to any point where we lose less than 5 minutes of data and get to it in less than a minute. And so we can rewind time and get to right before the ransomware hit or right before that file was damaged, and not take a long time to restore all that data. You know, we see companies when they're hit with different types of threats, sometimes are very resistant to go to their backups because, you know, it's going to be, you know, tens of hours or more of data restoration. Whereas with these snapshots, we're able to get back to any of these points in time in less than a minute. And then ZFS replication is also the fastest way to move large volumes of data. So even if we haven't retained that many snapshots locally on the system that's impacted, if we do have to restore from a remote system, the fact that ZFS replication isn't impacted by individual object size, it's not having to restore and sync individual files, it just restores the whole file system to the specific state. It means it will saturate the network as best it can the entire restore time so that your restoration will be as short as possible. So now let's get more into specifically ransomware and how to detect it and deal with it to protect your data.
So a recent Veritas survey of 2,000 US consumers found that 78% were concerned that businesses that were retaining their personal information would at some point become a victim of ransomware or other attacks of targeting sensitive data. And this is becoming more and more of a problem. You're constantly hearing about identity theft and security breaches at companies, and then you get an email saying, you know, we regret to inform you that we had a breach and your data was accessible. Obviously, this is something that nobody likes, and this is becoming more and more of a problem.
Yeah, especially when individual consumers have accrued 10 years of credit monitoring protection from the number of breaches that their data has been involved in. So how do we protect ourselves from ransomware? The first thing is realize what ransomware is trying to do, right? It's targeting any data that the compromised machine can reach, and especially network file servers. So even if it's not your storage infrastructure that gets hit with the ransomware, it's going to be, you know, endpoint machines. But because those have access, they're going to go through and try to encrypt all the files on the NAS or the SharePoint or whatever storage mechanism you have, and try to hit as many of those as quickly as possible. This is where ZFS snapshots can come in, because if we have snapshots, then we can undo the overwrite of that data with the encrypted version of the data and get back the original correct version. But it also can be a detection mechanism. If suddenly our snapshots are growing by, you know, tens of gigabytes, even though we're taking them every 15 minutes, then we know something is probably going wrong. So it can trip alarms about the problem, but also offers us the ability to roll back from ransomware instantaneously. You know, one customer we were working with was an educational institution, and one of the remote campuses got hit with ransomware, but via the point-to-point link, that ransomware managed to target a bunch of data at the main campus. And they were having to restore that data over a relatively slow point-to-point link. And it was going to take hours and hours. It was, I think, ended up taking 2.5 days to restore all the backups. And that's what led them to investigating using ZFS and knowing that next time we can get back to just before the attack in minutes instead of days, and have better recovery point objectives. We won't have to give up as much new data because we'll be able to take these snapshots much more frequently and much more quickly. But to that end, some ransomware has gotten smarter. Instead of encrypting the entire file, it purposely targets just the first and last megabyte of the file, and sometimes also one in the middle, to make sure that the file is unusable, but it doesn't take as long to encrypt all the files, right? If you have tens of terabytes of data, encrypting all of it will take a lot longer. Whereas if we just encrypt the first and last megabyte of each file, we'll be able to get through that storage server a lot quicker and ensure that the good guys have less time to catch on and to stop the problem. And that's why we want to, monitor those snapshots and see how they're changing and use that maybe as a detection mechanism. So if we can't rely on just the size of a snapshot as a detection mechanism, because maybe the ransomware has got smarter and not encrypting the whole file, what else can we do to detect ransomware? So the first is another tool that's part of ZFS and snapshots is ZFS Diff, which allows you to compare two snapshots or a snapshot in the currently live file system, and it will generate a list of the files that have changed. And so it tracks what changed about the file. So was the file renamed? Was it a new file, a deleted file, or was it a file that was just modified? By looking at this over time, we can detect unusual patterns, right? If normally we see files being added and files being removed, and maybe some files get modified, but suddenly we see a ransomware that renames every single file as it's modifying it to give it a different extension so that it won't open easily, then that can trip off an alarm and say, we've seen every single file being renamed as quickly as it can go through, and that can let us detect something. So by generating this list of changes and examining it and just having statistics on, 10 times the normal volume of files are being renamed right now. Maybe that's normal, but it's not, and that allows you to detect that. We can also do more in-depth analysis of the snapshots. So rather than just looking at the size of the snapshot, how much new data was maybe contained in it, there's a hidden property that's part of every snapshot where, or every data set, where you can ask, what is the amount of data that's been written since this snapshot? So instead of just each individual snapshot knowing how much data it's uniquely containing, this written property will tell us how much has changed. And so if we go back to, our monitoring system looks at since midnight or since 12 hours ago, how much data has changed. And if that volume is exceeding what is normal or even normally possible, that can allow us to deal with, or to detect that something unusual is happening and make sure that we stop it and that we can roll back sooner and avoid the disruption. So we have a question from the chat room. So Mark asks, can you use ZFS Diff to automatically avoid saving multiple snapshots where nothing really changed? You can, although the fact that if you have a snapshot and nothing changed since the last snapshot, it doesn't really have a cost. So there's not necessarily a reason to avoid doing it. But yes, you could use the ZFS Diff or that written property to decide that, this snapshot contains no new data, and so we can shorten its retention policy or just decide not to keep it. And so that very neatly brings us on to our last topic, which is how do I decide what my snapshot regime should be? And how many snapshots is too many? So the first thing we have to look at is looking at our interval. How often are we going to take snapshots? There's a small cost to taking a snapshot. It doesn't take up really any space, but because of the transactional nature of ZFS, when you take a snapshot, it flushes the transaction group as part of that snapshot. So that snapshot is everything that existed in that file system at that transaction. So it closes the transaction as part of making the snapshot. So while you could take a snapshot every second, it would hurt the performance of your pool. 10 to 15 minutes is very typical. Even every 5 minutes won't really impact performance. But if you get right up there and are trying to do it very, very frequently, it can start to impact performance. But taking a snapshot every 5 or 10 or 15 minutes is totally fine and very normal, and means that you're going to have really nice short recovery point objectives. Then there's retention. How many snapshots should we keep? Usually the limiting factor in this is really going to be the amount of space you have. But as long as you keep less than 1,000 snapshots per data set, then you're not going to have any performance problems. Unlike other systems like Linux's LVM, where taking a snapshot is going to have the performance of the file system, and each additional snapshot is going to take off another 20%, ZFS snapshots don't impact performance. If you have more than 1,000, it will take longer to list and manage the snapshots, but reading and writing from the file system will not be impacted. So just aim to have under 500 snapshots per data set, but that's per data set. The total number of snapshots in the pool is irrelevant. It doesn't matter. You can have 100,000 snapshots in the pool and it won't hurt anything. It's just you want to keep the number in any individual file system to under 500 or 1,000, and you won't see any problems. And so, yeah, your biggest limitation there is going to be storage space. Eventually, you're going to have to delete the oldest snapshots to avoid running out of space. But the one other criteria is that when you're doing replication, you need at least one snapshot in common. So when you're doing incremental replication, the starting point, both ends of the replication have to have the starting point, and then you can advance the remote side to the newer snapshot. But if you don't have any snapshots in common, then you're going to have to start replication over again, and that's costly. So finally, to cap us off, let's take a look at the outcomes we get from our data protection schemes.
Yeah, so as far as recovery points go, with less data loss, obviously our recovery point is going to be faster because there's actually less to restore.
Right. So if we make our snapshots more frequently, then our amount of data we're going to lose is less, and that'll give us a better outcome in the end.
And because we made those snapshots more frequently, we also have a faster recovery time because there is obviously less data to recover that would have changed in that time, also speeding us up. The third would be history. Having more history gives us a greater chance of recovery for events that are not detected right away, because sometimes things happen, you don't recognize that there's been a problem. And the more snapshots you have, the further back you're able to go and recover data. So this is very helpful because it helps you recover data that you don't initially realize there may be a problem with. And then lastly, we have space. So because of the copy on write nature of ZFS, snapshots allow replication of data that has changed, and you don't need to send every single bit of the file. So if you have a 10 terabyte data set, but only 10 gig has changed, you don't need to send and check 10 terabytes of data. You can just do the 10 gig that has changed, which obviously is going to speed up your recovery time, and you're going to have a quicker recovery point.
Yeah, and that's another advantage over the file-based backup. In the file-based backup, if any bit of a large file changes, it's going to back up the whole file every time. Whereas ZFS is at the block level, it knows, only the 8th block in this file changed, so it's only going to back that up. So it means less bandwidth, and it'll be faster to recover, but also it will take less space in total, allowing us to keep more history. Okay, so if you'd like to look at setting something like this up for yourselves, then do get in touch with Klara. So with Klara's ZFS subscription, you get access to our team of experts, administrators, and developers to help you with any of your questions, whether it's best practices about backups and setting up your snapshot regime, or just maintaining your storage and making sure you get the full power of ZFS out of your hardware. And we help you resolve any problems that you encounter. If you've not built your ZFS storage array yet or are looking at building a new one, check out our storage design and implementation service, where we'll give you advice and assistance with picking the right hardware, setting it up in the best configuration. Which of those parity things should you use? Is it RAID Z 2 or 3, or should you use mirrors? What's going to be best for your workload? And help you get it deployed and part of your infrastructure and integrated with whatever else you're trying to do, whether that's hooking it up as the backend for VMware or Veeam or whatever else you're trying to run. So questions. I see Matt has another question. He says, discuss the pros and cons of encrypting the root file system. And can you install FreeBSD on ZFS with native encryption yet? So it again depends on what you're trying to protect and what your threat model is. The disadvantages to encrypting the root file system, where the operating system and the configuration are, is that it's going to require access to the key at boot, and most times you want your storage server to be able to come up unattended, so that if it has to restart for whatever reason, that it's not offline until somebody can come and enter the keys. And so generally don't recommend encrypting the root of the file system, and instead having individual data sets that contain sensitive data and key managing those separately. And generally there isn't that much that's sensitive in the operating system configuration itself. And currently it is not possible to boot from an encrypted volume anyway, especially since that usually involves a key file if you want to try to have it headless, and the bootloader isn't necessarily going to have access to that. Although we are investigating looking at using the TPM, the Trusted Platform Module, in built into the hardware to be able to manage keys for this. If you're interested in that, definitely get in touch with Klara. So actually, to that point, if you are interested in that, make sure to reach out. You can hit our website, klarasystems.com, or email us, or reach out on Twitter, and we'll talk to you. All right. I think we have time for maybe one more question. Yep, there's one. So they ask, can you delay jail startup for an individual data set ZFS keys? For example, having one per jail. Yes. Klara upstreamed a key management tool into FreeBSD called ZFS keys that can allow you to prompt or get the keys as part of the startup process, so that you can delay the jails trying to start until you've mounted the file systems, which first requires loading the keys. Okay, I think we have about 30 seconds left. Time for maybe one more question. No, okay. Thanks everyone for attending. See you next time.
Yeah. See you, everybody. Have a good day.